So welcome everyone to our Instructor Training Center Scaling Networks course for the week of today is the November 2nd. You can officially start listening to Christmas music without being too embarrassed. I think my wife started a week ago, so she's ready for it.
Yes.
Most definitely. We are going to talk today about dynamic routing as this leads us into discussions of EIGRP and OSPF. Some of the content in this particular chapter is really review from semester 2 or from our routing switching essentials. We're going to talk about the difference between difference between metrics and administrative distance and some of the metrics that we use in routing protocols. And we're going to look at this chart, which is a very important chart when we talk about routing protocol classification. We talked in depth, even in this course, about static versus dynamic routing. We talked about how static routing has its place. There's no doubt that static routes, if you only have one exit interface, or if you've only got a very small network with a very limited number of networks that you need to route to, that you can get away with static routes. But as we expand, the very purpose of this particular course, as we begin to scale our networks and they get bigger, we need to start looking at dynamic routing protocols. So we can do automatic exchange between different routers on a big network. Now, one of the things that the very first item you see at the top of this page here is that they are breaking these into IGPs and EGPs. Now, I've done this before. I think I've already told you about autonomous. Man, I cannot spell today. So much for that English degree. And I know that's spelled wrong, but I just, for the life of me, can't get it right now. But this is a group of routers under the control of a single administration running a normally single IGP. So it's interior gateway protocols. IGPs are within autonomous systems, within AS. EGP, of which there is really only one today, that is between ASs. All right, and for us that's BGP. There's only one of those. But that's the big difference here. That's how we define an interior gateway protocol versus an exterior gateway protocol. One is within an autonomous system. The other is designed to run between autonomous systems. Or in most cases, the way we look at this is between ISPs or between large networks or possibly networks that are dual home. I don't know if you've heard of that concept before. Have you heard of dual home? You know what that means?
I have.
Yeah, what does it mean, John?
You got two network interface.
Right. You have two connections to the internet. And most, it can be, we typically just say two connections to the internet. It doesn't have to be the internet. Now, you can have your own private BGP network, and so it could be two different connections into the BGP network, but we typically say two connections to the internet, and that's normally through two ISPs. And you do that so that you've got redundancy. So if ISP 1 goes down, ISP 2 is still up. But that is the exterior gateway protocols. And for us, I'll go and tell you straight up, the only one we're going to talk about is BGP. There was in the past a protocol called EGP, exterior gateway protocol, but BGP version 4 especially, has completely taken the place of all other exterior gateway protocols. This protocol that we will cover a little bit in our connecting class, and we'll talk about how to do a simple neighbor relationship with BGP. This protocol is the focus, a great deal of the focus of CCNP route, and it's one of those protocols that is extremely powerful and also extremely dangerous. So you can cause some major issues with BGP if you're not careful. But we'll talk a little bit about path vector routing protocols, BGP, as we move forward. For us, and what we're going to concentrate here, we're going to talk about these interior gateway routing protocols. And they are the protocols that work within an autonomous system. We've got distance vector routing protocols, which are protocols designed to look at paths to networks based upon their distance, based upon a metric, and the vector, or the way that you go to get to that network. You then have link state routing protocols that we'll talk more about also in this section. But these link state protocols cause the router to look at the state of the links and the networks they're connected to, and then they send that information out, and all of the other routers in the link state routing environment will build a topology table, and then that topology table is then used depending on what algorithm you're using, which for OSPF it's shortest path first. That is used to then build a route table of the shortest path. One thing they mention on the right, but they don't mention on the left, is the concept of classful versus classless. Now, I'm going to tell you, a classful routing protocol does not carry subnet mask information in the route table updates. That's what makes it classful. In other words, if it has the subnet 192.168.12.0/30, okay, which is literally the usable addresses 1 and 2, and it's the range of 0 to 3, a classful routing protocol would advertise this as this network because it assumes it's a class C. Therefore, it cannot know that it's a /30. It simply assumes that it is the classful mask. Now, in today's modern world, that's not going to work because we use BLSM. So remember, here's one thing. Classful routing protocols do not support BLSM. Classless routing protocols.
So those routers do not do ANSI, right? They just look at the first bit.
Correct. They just look at the actual, they look at the network and they look at it from a classful standpoint. Is this an A, B, or a C?
Okay.
And then it will advertise that. And we're going to see where that causes issues here in a minute because they can cause some serious issues on your route table. A classless routing protocol carries subnet mask information. Oops. In the route table update. And therefore, it supports BLSM. In other words, if you had a classless routing protocol like OSPF, and you had the following networks, 192.168.12.0/30, and you had 192.168.12.4/30, those individual subnets will be what is getting advertised, not the major network of 12.0, because the subnet mask information is carried in the route table updates. So when we look here and we see that RIP v1, it is a distance vector routing protocol. It is an interior gateway routing protocol, but it is a classful protocol. It's legacy, which means it cannot support BLSM. And if you look, and I'll pull this up real quick. Let's see if I can't do this. RIP v1 route update. Let's see if I can find the actual RFC. Oh, that ain't gonna work. Sorry, I should have had this already pulled up, folks. But if you've never seen RFC, this is one of the RFCs for RIP. And let me see if I can find the. Here it is. You'll notice here is the routing information protocol RIP v1 route table update, the diagram, the datagram. Command version must be 0, and you see here address family identifier must be 0, IP address must be. There's nothing here that holds the subnet mask. There's no room in the RIP v1 IETF standard. But if we look at RIP v2 IETF RFC. Let's see if this is it. Should be it. I should better find it down in here. Let's see, where'd it go? And I know this makes riveting. And I think it's here. Here's the protocol extension for RIP v2. You'll notice that unlike the RIP v1 header, okay, so here's the RIP v1 update datagram. Notice there's no subnet mask information here. RIP v2 has a spot for the subnet mask information. So that is why RIP version 2 is classless. It carries subnet mask information. And RIP version 1 is classful because it does not carry subnet mask information. All right? Does that make sense?
Makes sense.
All right. Now, as we look through here, there are a couple of these protocols that you really are, they're legacy. IGRP no longer even is supported in Cisco iOS, but it was a class full distance vector routing protocol. It was a predecessor to EIGRP. Enhanced Interior Gateway Routing Protocol is, in fact, a distance vector routing protocol, and it is classless. RIP v2 is classless, although I will tell you this, we'll learn that RIP v2 acts like a classful protocol unless you put in a command no auto summary. We'll also learn that EIGRP, for many, many years, this was described as a hybrid protocol, but it really is not, and it is still purely a distance vector routing protocol that borrows some linked state concepts like triggered updates and triggered updates and non-periodic sending out of the update table. Link state, OSPF, and ISIS, they are both classless routing protocols, as is BGP, so they all carry subnet mask information. Are there any questions on these classifications?
Yeah, actually, oh, go ahead, Scotty.
Sorry. The difference between distance vector and link state?
The difference, we'll get to that in just a minute.
Okay, good.
We'll get to that in just a minute.
My question is the OSPF and the ISIS. OSPF, is that proprietary to Cisco or?
No, no. OSPF is an open RF IETF standard. So that's why you actually find many vendors run OSPF instead of EIGRP, because EIGRP is Cisco proprietary.
Okay.
Now having said that, EIGRP, Cisco has submitted EIGRP to the IETF to be an open standard. And technically, I now think that it has been validated to be an open standard, but no one else that I know of has implemented EIGRP. So EIGRP, even though technically if you go look right now, there may even be an IETF standard that for EIGRP, really the only people to still run it, or the only people to run it are Cisco. And then ISIS is also an open standard. And BGP is an open standard.
We don't. I've noticed I haven't done any of the ISIS in the lab. So
nope. And that is actually a protocol that was in the CCNP route class for many years. It went away. It's come back a little bit because it's used in MPLS clouds and service providers. They use ISIS, but many of them are now using OSPF too. So it's kind of it's a protocol that's in a weird state right now. I haven't read a lot about ISIS use. So yeah, be aware. We're not going to do anything in this class with it.
Okay.
If you move forward, go ahead.
That was my question, I guess, is where will we headed? It's OSPF2 that you can work with MPLS then.
Well, it's OSPF V2 and V3 both, because V3 supports IPv6. So if you're running MPLS file with IPv6, technically that'd use OSPF V3. But then again, how many people are running IPv6?
Not very many.
Not many at all. Exactly. So the funny thing is, as you look across this entire bottom row here of protocols, the only quote non-proprietary, or excuse me, the only proprietary protocol is the EIGRP. And again, just real quick, let me do something. Let me consult the Holy Google.
From a network administrative standpoint, the BGP, that would be only used by network admins that work for internet service provider, right?
Say again, you're saying BGP is for just service providers?
Right. Or is it?
You can't really say that, because There are some very big organizations, say U.S. government, DOD, that run their own private BGP clouds.
Okay.
It's not common. So typically you would say, if a student asked, I would say in most cases BGP is a protocol that is only run between ISPs.
Okay.
But there are some very large organizations that have their own BGP cloud.
Okay.
So, and here you see in 2013 that they've sent it out. They've released it to ITF as an informational RFC. So technically, it's supposed to become an RFC and an open standard, but I don't think anybody's going to adopt it because, quite honestly, we've got OSPF. So why adopt, a distance vector routing protocol when you can use the link state? And we'll talk about those in a minute. Oh, any other questions? I'm sorry. Any other questions on these?
No, I'm good.
Scotty, good?
I'm good, thank you.
Okay. So again, here's IGP and EGP. So interior gateway protocol within the AS and between the AS is where we run our exterior gateway protocols. Right now, BGP is beyond the scope of this course, but you will get it in your connecting course when you take the next course. Now, let's talk about distance vector routing protocols versus link state. For distance vector protocols, you determine how far a destination network is based upon a metric. And let's go over again what a metric is. And I'll give you a great example. Today, we had to go pick some gear up in Charlotte, and the three guys and I decided where we're going to eat lunch. We were trying to determine how we were going to eat or where we were going to eat lunch. So we started thinking about lunch, and we said, first off, what kind of food? All right. Do we want Mexican? Do we want just burgers? Do we want Italian? Okay. We then said, well, where is it? We were in a certain place in Charlotte, so we're like, location. That was one of our metrics. We then said, how much? Okay. Cost. How much does it cost for the food? And then we talked about, of course, quality, service, those types of things. Now, I'm about to fall asleep in my chair because we went to Five Guys and I ate a huge hamburger and too many fries. So, but these were all metrics that we used to figure out where we were going to have lunch. For routing protocols, metrics are used to determine how to get to a network. That metric can be hop count. In other words, how many routers do I go through? That is a metric. It can be an item such as cost, and that can be based upon the speed of links. It can be delay. It can be bandwidth. They're all different ways of doing metrics. For RIP has a metric of hop count. OSPF has a metric of cost. EIGRP uses a metric of bandwidth plus the sum of the delays in the path. So that's what a metric is. Now, in distance vector routing protocols, when they go to determine what the best path is, they use their metric to figure out how far a network is away, and then a vector of what interface do I go out, or what's the next hop IP address I got to go to in the path to get to the destination network. Now, here's an important concept. Notice R1 doesn't know about anything that R2 is doing on the other side. Now, in this case, the network is one hop away. But if this network was 3 hops away off of another router, R1 only sees the path based upon its vector. It doesn't have an overall view of the topology of the network. That is a key point with most distance vector routing protocols. And one of the reasons why EIGRP is weird, because EIGRP does keep a topology table, which is a link state feature that was integrated into EIGRP. But it still uses distance and vector to figure out how to get to a particular network. And that's why you look at RIP v1, RIP v2 are both distance vector routing protocols. RIP v3 is also, IGRP is also, there's no RIP v3, sorry. And then EIGRP is just an advanced distance vector routing protocol that borrows some link state traits. Link state's different. Link state goes and actually can flood the network with its information. And so in a linked state network, instead of only understanding paths based upon their neighbors and where they're going towards their neighbors, in a linked state network, the routers can actually understand the entire network because they have a linked state database, a linked state topology database, and they can understand all of the different networks and their links on the network and how to get to them. OSPF and ISIS are both linked state routing protocols, and we go through both the protocols coming up more and more. Now, here is one other thing I will tell you real quick. Distance vector routing protocols tend to send out periodic updates. For instance, RIP version 1 and 2 will send out their entire route table every 30 seconds, regardless of whether or not there's any changes. They also are routing by rumor because you don't talk to every single network or router in the network. You only talk to your neighbors. And for that reason, they can suffer from things like there's a couple concepts, split horizon, routing loops, those items that can be a little more prevalent among distance vector routing protocols than linked state. Because with linked state, you build that database and talk to all the other routers in your network. So you have an overall view of the topology. Linked state routing protocols flood the network, okay, upon boot up with their linked states, and then only send out updates if there's a change. So it's a triggered update instead of periodic updates. And that makes linked state protocols typically a little more bandwidth, less bandwidth intensive because they don't flood the network every X amount of time or some periodic interval with their entire route table. Now, we talked about classful and classless. Now, take a look at this. This is where you could really get in trouble, running a classful routing protocol. So, R1, let's say it's running RIP version 1. R2 and R3, they're all running RIP version 1. Well, when RIP v1, when R1 sends its updates every 30 seconds, it's going to advertise that the network 172.16.0.0 is available on R1. So, R2 is going to put that in the route table. Okay, it's available via this 192.168.1.1. Well, the bad news is R3 is going to do the exact same thing because remember, it doesn't know the /24. It only knows, hey, this is a class B, which means it should be 172.16.0.0. And so it sends it R2. And now R2 thinks that the 172.16 network is available one hop away via R1 and one hop away via R2. And what's going to happen is you're going to get some pings that work, some pings that don't work. And it really depends on how Ceph is, if you've got Cisco Express forwarding set up and how that's being used to build the Ceph table. If this was a classless routing protocol, it wouldn't be a problem because you would have, you send the update out, I'm sending out the actual network. So I'm sending out /24. So that goes in the route table. R3 sends out /24. That goes in the route table. And now you've got two separate routes, 1 to 1.0 off of R1, 1 to 2.0 off of R3. And your pings are going to work because you have a correct routing table. RIP v2, EIGRP, OSPF, and ISIS are all classless routing protocols. RIP v1 and IGRP are classful. BGP, by the way, is also classless. Any questions on this? You can see how that causes problems. No questions?
None.
All right. So here's just a quick comparison chart. Hey, Larry. Quick comparison chart. You can see RIP v1, RIP v2, IGRP are all slow to converge. Converge means all the routers have a consistent state of the networks in the internetwork. The IGRP, OSPF, and ISIS are fast, very fast to converge. Scalability, obviously RIP v1, RIP v2 have a 15 hop count limit. So if you have more than 15 routers, you can't use RIP v1 or v2. It just won't work. EIGRP is large and also the same for the others. The resource usage low for RIP v2 because think about how simple the metric is. You literally add together the number of routers that you go through, and that's your hop count. With EIGRP, you've got to actually go through and look at the bandwidth plus the sum of the delays to each network to figure out your metric. And in OSPF, you've got to build a topology table, and you've got to do the same thing with EIGRP, build a topology table. Then you have to run through your algorithm. So there's pretty high resource usage on those two. And then you look at your implementation. It's very simple to implement RIP v2. And as you move up, it's a little more complicated to do EIGRP and OSPF. It's not crazy hard, but it's a little harder. All right, I'm going to just quickly, I've already talked about metrics, but hop count is RIPs. OSPF is cost based upon the bandwidth of a link. And then EIGRP uses, they put here bandwidth, delay, load, reliability, MTU. However, in the formula that we will learn as we get into the chapter on EIGRP, you will see that all of these actually end up being zeroed out except for bandwidth plus the sum of the delay in the item. So one thing I will tell you is this. Remember, these are the metrics used to find the best path within the routing protocol. But what if I had let's imagine that these routers, all these routers are running all three protocols. So RIP, OSPF, and EIGRP. And I'm trying to find on R2 a route to this network, 110.2.16.3.0. Which one from these three routing sources, which one would go in the route table?
All three?
Nope.
Well, EIGRP would take precedence.
Bingo. And why would it take precedence, John?
It's going to have a more reliable, more believable path.
Well, it's called administrative distance, right?
Okay.
Remember our administrative distance? That is the Cisco, I can't say entity, but Cisco.
Rating or something?
Well, yeah, it's not rating. I'm going to say factor, used to pick between multiple routing sources. Let me ask you this. So I've got a route with RIP, I got a route with OSPF, I got a route with EIGRP, and I got a route with static. Which one goes in the route table?
Static.
Static, yeah, because what's the AD of RIP?
120.
120. What's the AD of OSPF?
110.
110. What's the AD of EIGRP? By the way, why do I call it D? Anybody know? If you look in the route table, it's a D because it uses the dual algorithm, the fusion update algorithm. What is it?
90.
90. Okay, and what are static routes? 1. Okay, or 0 if they're directly connected, which are still technically 1. So if I had a route that was static, it would go on the route table. The other ones would be there only if the static route goes away. And if I had routes didn't have a static route, the EIGRP route would go on the route table unless this route went away, and then it would pick up with OSPF. So, and why is EIGRP considered better than OSPF? Cisco proprietary protocol, and it's their operating system, so they did it that way.
So it doesn't run all three protocols and have a table for each one?
No, there's one route table. Okay.
Okay. So
what would actually be happening is you would have the RIP information. You would have an OSPF topology table, and an EIGRP topology table, but you only have one route table, and only one of the routing source informations can go into the route table.
That clears it up. Topology.
They're still running, but only one of them gets picked to move forward into the route table. And again, the good news is if you had any of these go down, so like I said, if EIGRP quit working for whatever reason, or if that route went away, then OSPF could be placed into the route table. It had to go back through a calculation and put OSPF into the route table. Okay? All right, I'm going to move through that, and there's our metrics. So dynamic routing protocol information, basically you take your, it depends completely upon the protocol as to what's going to be used, but you're going to look at your routing protocol information, you're going to determine the best path, and then send that information out to your other routers, and then that will be shared. Now, again, it depends upon this. We're going to look at running RIP v2 in this particular instance. So they're going to boot up. They're going to look and find their directly connected interfaces first. See how they're finding the hop 0. In other words, those are the interfaces that share the C and the L. Obviously, the L is put in there as the actual interface. So that's what happens when you first start a distance vector routing protocol. It will then send that information out to all of its neighbors. And that the neighbors will then integrate that into their route tables. Okay? So each one of the routers will do the initial exchange and send out information about the networks they are connected to. And then those will be placed into the neighbor route tables via the updates. Now, one of the things that technically RIP v2 and RIP, they're not supposed to do triggered updates, but there was no RSC or IATF standard saying it could not do triggered updates. So be aware that RIP sends its entire route table out every 30 seconds, but it also, the implementation found in the iOS, will also send out updates if you make a change. So it doesn't wait the full 30 seconds to send an update out. But by standard, RIP does not have to do that. Okay, it is not required. The important thing to hear to notice about RIP and distance vector is note that R1 never sent its information all the way to R3. R1 sent its information to R2, then R2 passed that information to R3, and vice versa. This is why we sometimes call distance vector routing protocols routing by rumor, because if you've ever played that game to where you start a rumor on one side, or you tell one person in a class something and have them whisper it all the way around class, by the time you get to the last person, it is completely different than what you originally said. That is one of the problems that can occur with distance vector routing protocols, is that they don't have a full view of the network. So, Scotty, you asked about the difference between distance vector and link state. One of those is that it's viewed. Distance vector routing protocols only have a view from their neighbor. They don't have an overall view. They also flood their table every X amount of seconds, depending upon the routing protocol.
All right, so how does the administrative distance come into play when you're trying to put the best path in? Is it using administrative distance, or is it using hop count, or is it using cost? Okay, good point. Here's what it does. It uses, in this case, because everybody's running just RIP, we're determining our best path based upon the metric for RIP, which is hop count. If these routers were running 2 or more routing protocols, so again, remember, metric is used within a protocol to pick the best path. Okay. Administrative distance is used between protocols to determine what best path gets put into the routing table. Let me put that on note. So metrics used by routing protocols to find the best path within a single protocol. So for RIP, that's hop count. For OSPF, that's cost. For EIGRP, again, it's a very long thing, but it ends up being bandwidth plus the sum of the delays in the path. Okay? So that is within a single protocol. Administrative distance used to determine what routing source will go into the route table. That helps.
So that is between routing protocols or sources, because it could be static, and that's not a protocol, it's a source, okay? Or it could also be connected, which is, again, not a source either, that's connected. So does that make sense?
Yeah.
Okay, good. All right, convergence is when convergence is when you have full reachability. In other words, you can ping from one end all the way to the other end and back. One thing I will teach you about routing protocols and about routing in general is all routers make their routing decisions based upon their route table alone, period. Doesn't matter whether or not R3's got a route or R2's got a route. If R1 doesn't have a route, it will be placed in the bit bucket. The packet will be thrown away. So all routers make their routing decisions based upon their route table alone. Just because there's a route to the destination network doesn't mean there's a route back, okay? So be aware of that. That's a very important item too, because I've seen many, many times where people get their routing and the ping is actually getting to the opposite side, but R3 doesn't have a way back to R1, and you get a failed ping in the end. So, some of our distance vector routing protocols, RIP-v1, RIP-v2. RIP-v1 sends out, and RIP-v2 sends out every 30 seconds an entire route table. By default, RIP version 1 broadcasts to the all 255 IP address. You're going to learn that RIP-v2 multicast. Okay. So you've got sending and receiving updates. You've got calculating best path and detecting and reacting changes. That's what the distance vector algorithm can do. And it looks at the distance to a network and the path. So we're kind of going back over the same thing again. RIP does use the Bellman-Ford algorithm, which is developed in 1958 and 56. So it's really a very simple algorithm, hop count. And then IGRP and EIGRP use the diffusing update algorithm, dual, which is why, if you've ever wondered why EIGRP routes have a D in the route table, it's because of the fact that they use the dual algorithm. So here we go. RIP-v1 does not support BLSM, does not support CIDR or classless interdomain routing, does not support summarization, does not support authentication. You really should never use RIP-v1, straight up, okay? It is a simple distance vector routing protocol that broadcasts to the all 255s when it needs to send out any of its information. RIP-v2 uses the multicast address 224.0.0.9, and it does support BLSM CIDR summarization, and it does actually support authentication, which is very important for modern routing protocols because it provides security so that someone can't just drop a router into your network and start pulling updates off the route table. So I will say whether or not that's ever been done before, but it's been done before. I don't even know why they bother to show you IGRP, but EIGRP uses 224.0.0.10, and it is classless. It does have a maximum of 255 hops. Now you can actually use networks that are bigger than 255 hops, but you also can use what's called an autonomous system number, and it's a little weird. When we actually configure it, I'll show you. But it's more like a work group name than it is anything else if you're familiar with the old Windows ideas. EIGRP does, however, have some link state features, such as bounded triggered updates. In other words, EIGRP doesn't send its route table out every X amount of seconds. It only sends it out when there are changes. Now, there is a timer at a certain point where we'll send it out, but for the most part, it only sends it out when there's a change to the route table. It does have a keep alive mechanism, so it actually sends out hello packets to say, hey, I'm here, everything's good, I'm here, I'm here. It does have a topology table, which allows it to have a more, an overall view of the network, which you would not normally associate with a distance vector, which is one of the reasons why it used to be called a hybrid protocol, is because it does share so many features with link state routing protocols. This topology table you're going to learn is one of the reasons it has very fast convergence, because if there's a feasible successor route in the table, it can immediately move into the route table if what's called the successor or the best route goes down. We'll learn more about that as we move forward in the EIGRP section, so don't worry about that right now. And EIGRP does support multiple protocols, so it's got what are called PDMs, protocol-dependent modules. It even has its own layer 4 protocol that it uses to allow it to support IPv6, IPv4, IPX, and AppleTalk. All right, OSPF, or Shortest Path First, which are, by the way, OSPF and ISIS. They use the Shortest Path First. It uses what's called Dijkstra's algorithm, which is the Shortest Path First algorithm. So it builds the topology, it understands the entire topology, and then it looks for the shortest path to a destination. So for instance here, you would see that this is 25, 27 versus 10, 20, 30, 32 versus, you can see there are multiple paths, but it builds a shortest path, and then we'll put that into the topology and the route table. We'll talk much more about how this is built in OSPF when we get to the chapter on OSPF. But here's a good example. They show it to you, just trying to figure out the best way. R1 has multiple paths to different places. R2 LAN, okay, it's got 22. The R5 LAN is 27, so 20, 37. It should be 37. R5 LAN. Oh, it went. I'm missing something somewhere. R2 LAN is 22, I agree with. R3 LAN would be 7, I agree with. R4 LAN would be 22. Nope, hold on, 17, that's right. All right, I'm going to do this. Here it is, 5, 10, 10, and 2. So that's 27 for R5. So it's a little different. It goes here, 5, 10, 10, 2. Sorry, long day. It's Thursday, isn't it? That means tomorrow's Friday. Woohoo! So you can see R1's path to R5's network goes actually through here, because that's the shortest cost or least cost. And every single router builds its own topology table and has its own set of costs. It then uses each one of those, uses that to build its own shortest path first table. All right. So in a link state routing process, each router learns about its directly connected networks. In other words, each router finds out about its directly connected link states. It creates a neighbor relationship by sending out hello packets. It then sends out what's called, or floods, link state packets. And it floods it to all neighbors, and they then flood it, and it's then flooded out to all other neighbors. And that is used to build the topology table, which allows you to build this, which then allows you to build the shortest path first. And then you are able to build your route table. So here you can see, first thing R1 does is look at all of its different links. It's got this link, it's got a link here, a link here, and a link here. It's then going to take that information and find out who its neighbors are by sending out hello packets. We're going to learn about a thing called passive interfaces, so we're not sending out hello packets on an interface that doesn't have a neighbor on it. Once it learns that, it then takes the link state packets and sends those to all of its, floods it out to all of its neighbors, and they flood them out to everybody else. So it's going to get flooded out there, and then gets flooded to everybody. And all of the routers on the network learn about R1's link state. Very different than distance vector. Because remember, Scotty, with distance vector, you only send it to your neighbor, and then the neighbor takes it in and then forwards it. With this, notice how it's being flooded to the entire network, so that all of the routers in the network are aware of your link states. That is a major difference between distance vector routing protocols and link state routing protocols. Okay. It also means this. If you have a large network and all your routers bounce for some reason, so they all lose power and come back up at the same time, you're going to have a large amount of traffic to begin with, because as they learn about their link states and flood the network, you've got those LSPs flooding the network. So that's something that can actually affect your networks on boot up. Everybody then builds their link state database and finds the lowest cost paths, and then those paths are used to build the tree and you can actually walk through this and look at how they're each building their tree, every individual network. And then the lowest cost pass gets placed into the routing table. So use metrics to determine the best pass, and then that is placed into the routing table. And this is assuming you're only running one link state protocol, not multiple protocols. Why would you use link state protocols? Well, first off, they use triggered updates. They're scalable. They have an overall view of the topology of the network. And quite honestly, they've got a large amount of scalability due to their hierarchical nature. In other words, we're going to learn that you can take OSPF and you can create what are called areas. And so you can actually create an area within which network changes will not be propagated. Small network changes will not be propagated to other areas. You can do summarization to make sure that if a single link goes down, that doesn't get flooded out to every single area across your entire 4,000 site corporation. So it's got a hierarchical design that we will talk about. It also has these event-driven updates, which means you're not flooding your route table out to everybody. It only sends out LSPs or link state packets when there's an actual change on the network. There are some disadvantages, though. One is because of the fact that you're doing a more complicated algorithm, you're holding a topology database, and then you're having the routing table. It takes additional memory because you do have the link state database and the SPF tree. And at boot up, you can obviously have the LSP flooding, which can affect your bandwidth, depending on how fast your bandwidth is. So we get into that by doing areas. And this is where we can actually create multiple areas and then keep the LSP floods from going through it. We can actually keep the information inside an area by summarizing networks. And we'll talk more about that when we get to that in the OSPF section.
I noticed I got an area 51 in that one.
Yeah. Just be careful. It could disappear on you. You never know what may happen. I will tell you this. One of the things you're going to learn is that by design, all areas must connect to area 0. We're going to learn about a thing. They briefly mentioned a thing. It's a CCNP topic called a virtual link, where you can actually go. You can put area 6 down here on the other side of area 1 and then do a virtual link across area 1 to make it think it's connected to area 0. But for the purposes of the CCNA, all areas must connect to the backbone, which is area 0. But area 51 could disappear at any moment. OSPF v2 support for IPv4, v3 supports IPv6. And so you also will learn that OSPF v3 supports IPv4 and IPv6. They just talk a little bit about ISIS, which uses, it was developed by the ISO for use for the OSI protocol model. It's a weird protocol, really is. It uses all kind of weird nomenclature and naming. It's just it's a strange beast. But it is out there in ISPs and carriers, and it is part of the CCNP route now. But we're not going to cover it here. All right, not right now. We've got enough to do with EIGRP and OSPF. And folks, that is the end of chapter 5. Our next chapter will be, obviously, chapter 6, which is EIGRP, and then we will move into OSPF. So our next chapter will actually show you how to configure EIGRP, how it works, concepts such as feasible successor, those types of things. So I'm going to stop the recording. And